Welcome back. Now we're going to look at 6.3, which extends the table of Laplace transforms and introduces us to transforming linear systems. So the completing the square method is only required when we have irreducible quadratics where there are no real roots. Okay, so how do we expand this out? Well, by comparing the two denominators, I want to think of taking this s squared plus cs and first expanding that out by adding the next term that we need to have a perfect square. That would be this value divided by 2 squared. So that forms a perfect square by itself. And then since we added the c squared over 2, we need to subtract it on the outside, left over. And then I want to compare this to s minus a quantity squared plus b squared. Okay, so this side, when we collapse it down, we have s plus c over 2 quantity squared, because this c over 2 multiplied by s, I can think of it, we have 2 copies of c over 2 times s. They give us a c times s. And then we have the s squared, of course, and then the c squared, c over 2 quantity squared right there. Well, that makes equal to s minus a squared. So we have a equals minus c over 2. Now, we could have just expanded it as a equals c over 2 and have an s plus an a, but we'll want to work, it's sometimes helpful to think of this as shifting to the right, because we can use a property of the transformations to pull out an exponential. And then the other term, negative c over 2 squared plus d is equal to b squared, which means b is equal to the square root of d minus c squared over 4, or another way to think of it is square root of d minus a squared, because a is at negative c over 2, and if we square that, we get c squared over 4, so we can just subtract a squared out of it. So there we have a and our b. Okay, so that's the first expansion of the quadratic. Now let's look at the full transformation. Okay, so now let's look at the formula noted as equation 6.7 in the book. If our c squared is less than 4d, then the Laplace, the inverse transform of as plus b over s squared plus cs plus d has the following components. We first have an exponential we can pull out. Then we have a times the cosine piece plus this combination of little a times big A plus b over little b times sine of bt, where a equals negative c over 2 and b equals square root of d minus a squared. Okay, so let's prove this. The first thing you want to do is use the expansion using completing the square on the bottom. So we get S minus A quantity squared plus B squared. Okay. So now what we want to do is use the theorem in the book that translates shifted transformations. And that is theorem 6.2, which says that the transformation of e to the at times f of t equals f of s minus a. So we want to use this theorem that if we have a shifted transformation, we can invert it by pulling out an exponential. So let's first think of this function as a shift to the right by a. Well, we have the shift on the bottom, s minus a squared plus b squared. So wherever we see an s, we should group it as an s minus a. Well, here's an a times s on the top. So let's group that as an s minus a times little a times big A. But to do so, we'd have to subtract a little a times big A, and then we, of course, have to also add. So let me do a different color. Minus a on top, and then add little a big A to compensate for that, and then plus big B. Okay, so that sets up the shift. So our theorem says that if the transformation of an exponential times a function creates a shifted version of that function's transformation going backwards, if we find a transformation that is a shift, that means whenever we find an s, it is represented by an s minus a. We can undo the shift and multiply by e. So we pull out an e to the at. Now, what is f related to a big F? Well, that is the inverse of this function unshifted. So what once was f of s minus a now becomes f of s. So we get an a times s plus a little a big A plus b, all divided by s squared plus b squared. So this theorem, 6.2, is a property to unshift an irreducible quadratic. Turn it back into the pure oscillations. So basically what we're saying is we're turning an underdamped system to an undamped system multiplied by an exponential. Well, it's still underdamped. It's just that we're factoring that exponential out of it. Okay. So now we want to look at how this breaks up into the cosine and sine pieces. Well, the cosine piece is easy. There's that s. So let's see. A times the inverse of s over s squared plus b squared. So there's your cosine piece, a times cosine of bt. For the sine piece, we have a group of constants. So let's factor that out. Little a, big A, plus b times the inverse of. But for the sine function, we need to have a constant on top that matches the frequency, b. So we multiply by b and divide by little b, and it gives us an s squared plus b squared. And that, bring that up a little bit. That does it right there. So let's finish off the transformations using our table. Transformation of the inverse of s over s squared plus b squared is the function cosine of bt, which transforms to s over s squared plus b squared. And the inverse over here, multiplied by little a big A plus big B over little b, is the function whose transformation is b, the constant, over s squared plus b squared, and that is the sine of bt. There we go. So now we have proven that whenever you have an irreducible quadratic on the bottom, it'll convert over, that is, as long as c squared is less than 40, irreducible quadratic on the bottom, that'll convert over to an underdamped system. Duh, makes sense, right? Complex, a non-real exponential roots or eigenvalues. It must be underdamped, so we factor out the real exponential piece, and then we have the oscillatory piece, which is broken into the cosines and sines. And the real cosine piece has a simpler constant, and the imaginary sine piece, when made real, has the more complicated constant, but it's still all put together. There is our nice little transformation. Now this formula is a bit of work in general to use, so we only really use it when the reduction is a little bit complicated. If the completing the squares operation uses nice integer values, it's sometimes easier just to do the process by hand instead of using the formula. But you're welcome to use either